Okay, so we're going to be talking about high performance liquid chromatography, okay? High performance liquid chromatography. Now, this word here, performance, can also be replaced with another word. The other word is pressure, okay? Pressure. Now, the reason why we use the word pressure is because in this method, we also use a very high pressure. Now, what is important for you to know is this, that this method is used primarily for things which are sensitive to heat, okay? Which means that you cannot use the other instrument, which is called gas chromatography. So things which are more biological in nature, okay, things like maybe enzymes, proteins, basically things which are sensitive to heat, okay, sugars, those are the kind of things that you can use HPLC for. If you use gas chromatography, that one uses a very high temperature, so all of these things will either denature or they will caramelize. So in this method, basically what happens is you just need to know a few things here. You have a solvent system, all right, a solvent system. Now this solvent system, right, you can manipulate the solvent system. You can make it let's say 100% polar, or you can make it 100% non-polar, okay, non-polar, or you can make it anywhere between this, all right. So example, it could be like, let's say 70% polar, okay, and plus 30% non-polar. So you can manipulate the polarity of the solvent system. You can do that, all right? But for us, it's not important to know this. This is the column, all right? The column is usually very short, maybe about 15 cm, 20 cm, I think most to most maybe about 30 cm long, right? So from 10 cm to about maybe maximum 30 cm. It could be 45 cm as well, but we don't really need to know. So the columns are not very long, okay? Columns are not very long. And this is the HPLC pump. The pump produces a very high pressure. Sometimes the pressure can go up to about 100 times to 150 times atmospheric pressure, okay? So it goes up. So what happens is the sample is injected here, and the solvent system comes here and pushes it into the column using very, very high pressure. The column is usually a packed column. So packed meaning the entire column, which is a stainless steel tube, is completely packed, okay, completely packed. And your stationary phase, right, let's say, like for example, if this is your stationary phase can be coated with other chemicals, okay? It can be coated with other chemicals. So usually, like sometimes your stationary phase can be like silica, right? It can be silica. And then what is coated here, okay, whatever is coated here, it can be non-polar depending on what you're doing, or it can be polar, all right? So silica is usually like the base, and then you coat the silica with something else, okay? Then the separation takes place, and then is detected by the detector. So the detector basically detects who is coming out. Then at the end of the day, this is how your results come out, okay? This is how your results come out. And let me just very quickly explain this to you, okay? Let me erase this, okay? So your results will come out like this. This is how it will look roughly. So you'll see like a line like this, and then you see a peak like this, and then another peak like this. So let me just explain these peaks. So this basically means currently, you see, it means that whatever we have put into the HPLC, it contains two different compounds, okay? It contains two different compounds. Let's say this is compound number 1. Let's say this is compound number 2. Compound number 1 comes out at roughly about here, 5 minutes, something, maybe 5.8 minutes. And this comes out at about 10.8 minutes, let's say. So these are called the retention times, okay? These are called retention times. Retention time is basically how long a sample is kept in the column. So obviously this sample number 2 here is kept for a much longer time, which means that it's kept for, let's say it's kept for 10.8 minutes, right? Meanwhile, in this case, it's kept for 5.8 minutes. So we can say sample number 2 is strongly attracted to the stationary phase. So sample number 2 is strongly attracted to the stationary phase because it has a larger retention time. Meanwhile, sample number 1 is less attracted to the stationary phase and more attracted to the mobile phase because it has a lower retention time comparatively. And another thing that we can figure out here is if we can measure the area under the peak, right? This area under the peak will tell you the quantity of the sample, So you can see the peak number 1, the area is bigger. So it has a larger quantity, So that's basically how the graph will look like. The graph will look something like this. So whoever comes out first, whoever has a lower retention time is more attracted to the mobile phase. Okay. Then let's just very quickly look at gas chromatography. Now, gas chromatography, right, it is basically used for things which are not sensitive to heat, which means that things like alcohol, right, when you expose it to heat, it does not decompose. Or gases that come out from car exhaust or factory exhaust and things like that, right? So what happens is they do not decompose. So you can use gas chromatography. So in HPLC, the mobile phase was a liquid. Meanwhile, in gas chromatography, the mobile phase is a gas. And the gas that we use has the mobile phase, right? Okay, so this is the carrier gas. This is called a carrier gas. This gas must be inert. Okay, must be inert. So usually we use gases like argon, maybe we use neon, we can also use helium. These are all group 18 gases, so they are inert. Inert meaning they do not take part in the reaction. They do not react with the reactants, okay, whatever you're separating. Then this is the column, all right, this is the column. The column can be anything from 1 meter to, let's say, I dare say 100 meters. Okay, so you have you can either have a packed column, which is usually about 1 meter, 1.5 meters, and you can have columns which are very, very long. These are called capillary columns. Okay, I hope I spelled that correctly. Capillary, maybe there's a double L. Okay, wrong. For all reasons, maybe I've got this wrong. Okay, but anyway, capillary columns. So these columns are very thin. They almost look like hair fibers, but they can be wound into 100 meters. Okay, anything from 1 meter to 100 meters. So the column is kept in an oven. So the temperature of the oven can go anything from 30 degrees Celsius to up to maybe about 400 degrees Celsius. So you can manipulate the temperature of the column. So what happens is you inject your sample, right? So your sample can be a gas, okay? Sample can be a gas or a liquid that can easily become gas. So here is your injector pot, okay? This is your injector pot. This injector pot is often heated. It is heated maybe about 50 degrees to about 80 degrees or maybe even 100. This is to ensure that all liquids that you put in are immediately vaporized. Okay, So they go through the sample, they go through the column, all right? And usually the column can be it's usually a wall coated column, or maybe if the column is very short, it could be a packed column. All right, we don't have to worry too much about that. So the separation happens here, and then it comes out and is detected. Same concept like just now. All right, the more peaks that you see, that means there are more compounds, and anybody who comes out first has stronger attraction to the mobile phase. Now, usually in gas chromatography, right, separation is based on molar masses. So another way that we can look at it, especially for gas chromatography, is this. The compound that comes out first, right? This compound, the molar mass is lesser than this compound. So this molar mass will be higher. Okay, for example, maybe this gas is let's say this gas is oxygen and this gas could be carbon dioxide. So the heavier gas usually comes out later. Okay, that's another way of looking at when we talk about gas chromatography. That's what we do. All right, that's what we do. It says here inert gases, you can even use nitrogen. Yeah, because nitrogen is also an inert gas. It doesn't easily react with samples. Okay, but we usually prefer using group 18 gases because they are relatively inert. Okay, so I think that's about it. Okay, so if you look over here, you have octane and you have nonane, right? Octane is C8 and nonane is C9. So C9 is a little bit heavier, so it takes a longer time to come out. Again, the peak, the area under the peak will tell you the quantity. Okay, so that's basically the difference between gas chromatography and the other one was HPLC. So gas chromatography is used for things which are gaseous and things that do not decompose when exposed to heat. All right. So what is important for us is to be able to look at this chromatogram and then decide what is happening. Okay. All right. We stop here.